Can everyone hear me? Oh, I can hear myself. I know you can hear me. All right. So, as was already mentioned, my name is John Stevens, and I am the co-founder and CTO of a new smart contract verification company called Veradice. And today I'm going to tell you about some of our tooling that we have available, which includes ways to perform attack synthesis for DeFi applications. And so first I'm going to start with just an overview of our tools. And so what you can see right here is just kind of the tools that we have available at the moment. And so one thing that I would like to point out is, we are not working only for Solidity. We are attempting to build analysis tools regardless of the particular blockchain infrastructure you're working on. And so that means that someone can provide us with a Solidity file, an Ink file, Rust, whatever, and then also specify the particular blockchain that they're targeting. And then we'll treat those files the same, and they will go into our analysis infrastructure. And so in the back end, it's going to be translated into LLVM for those who are interested. And then it goes into the tools that are shown in I don't even know where my pointer is, into that block right there. And so the first thing that's done is we'll look for common vulnerabilities. So these include like reentrancy, flash loan attacks, stuff like that, using static analysis. And then if we don't find any vulnerabilities, then we go on and we perform formal verification. So if the contract that you're interested in verifying is some sort of specific contract that we know about, so for example, an ERC20 contract, we can verify against a certain set of properties that should hold regardless of the implementation, but also we can take in user-provided specifications and verify against those. Now, the important part here is if everything checks out, then that's great. We don't really have a whole lot to say, but if things don't check out, that's where we do something a little bit more interesting, which is where we try to produce concrete evidence of exploitability. And so what that means is we send it to our attack generation engine. And so what our attack generation engine does is it will look for a specific contract that is capable of using the exploits that we found in previous steps in order to basically attack the contract that the user gave us. And so this not only provides feedback to the developers so that they're able to get evidence of exploitability, but also they can kind of see the impact of what would happen if someone was able to exploit their contract. And they can also check and see, if I eventually end up fixing this, can the contract that was given to me by Veradice still attack the contract? And so, once all of this is done, it's bundled up into a report, normal stuff, where it contains the list of vulnerabilities that were discovered along with any concrete attacks that we were able to find. So let's go ahead and take a look at how this works. Oh, actually, first, let's a couple of things to point out. As I already mentioned, this is blockchain agnostic. As far as we're aware, this is the first blockchain agnostic analysis infrastructure. And second, this is the first attack synthesis infrastructure for DeFi. And I'm also going to only be talking about those two components today. So the common vulnerability detection is wrapped up in a tool called Vanguard. The second component, which is down at the bottom, the attack generation, is wrapped up in a tool called Eros, and today I'm going to show off both of those tools. All right, so Vanguard is what we're going to start with. So it's going to do common vulnerability detection, which means it's able to detect things like reentrancy attacks, flash loan attacks, arithmetic overflow and underflows, and stuff like that. A couple things to note is it is one, blockchain agnostic. I'm going to say that several times during this presentation, so if you get tired of me saying it, too bad. Second, it's got a low false positive rate, which means that if we do report a bug, then it's very likely a bug. And then third, it is extensible. So if we have not written a detector that you're interested in, then, well, you can do it. So we're first going to take a look at this tool. And so what I'm showing right here is just a smart contract that's written in Ink. And so I know this is Solidity Summit, why am I showing this? But bear with me, we'll get to the Solidity in a second. So this is just a wallet contract, and it has a canonical reentrancy vulnerability. So if you look right here, there's an external call followed by a modification of the state that tracks what users are supposed to get paid back. And so we can go ahead and send this contract over to Vanguard. And so cross your fingers. And so first it's going to end up compiling the contract, and then it sends it over to Vanguard and gives you a list of the vulnerabilities. So here we see that within the withdrawal function, which is exactly what we were looking at, there is a reentrancy vulnerability in the wallet contract. And then we can also go and change this contract to be correct. And I apparently already have it open. So let me just, I can increase the size of this, I guess. And so these were the lines of code that we were looking at before. So let's just go ahead and fix this really quick. Very easy, done. And then we can rerun that detector. And now you can see that it's not reporting a reentrancy vulnerability because we ended up fixing that, that particular reentrancy. So let's go back to the slides. So that just showcases our, basically what we can do in Rust. Now let's go ahead. I promised you Solidity. Here we have Solidity. So here what we have is we've got an example lending pool. And so what this lending pool is going to do is it allows people to borrow tokens as long as they provide a certain amount of collateral. However, as we've heard about recently, there's this thing called a flash loan where someone might have a large number of tokens and they can manipulate the price of a particular asset. And so here, this particular contract is vulnerable to that because if someone has a large number of tokens, they can inflate the denominator of this division right here, and that could end up causing the amount of collateral required to return 0. And that would be particularly bad because that means that someone could potentially borrow money without providing any collateral, and therefore they have no reason to end up returning the tokens that they borrowed. And so this is something else that we can detect using our Vanguard tool. And so here we're going to look for a flash loan attack in that contract, and it is running. And so first it's going to do a little bit of pre-processing, and then it spits out, yes, the borrow function, which if we go back over to the slides, is what ends up, where you end up performing that, where you end up calculating the price. So what the user is going to interact with is vulnerable to a flash loan vulnerability. And so here, I'm not going to show you how to fix it. Instead, I'm going to show you what happens once we know there is a vulnerability in a particular piece of code. And so once we know that there's a vulnerability, I told you that we have this attack synthesis thing. And so now I'm going to show you what that looks like. And so once there is a vulnerability, we can start asking questions about how this vulnerability could be used. And so in this case, we're going to generate a query, and that query is going to be translated into some machine checkable language. So in this case, we've got a domain-specific language for specifying these queries. And in this case, we're saying, if there were to be an attacker, after they finish their attack transaction, we want to see if it's possible for the balance or the number of tokens the lending pool owns to be 0. And so if it is 0, then that means that they were able to take all of the tokens. And since the lending pool has a large number of tokens, it would be very hard to do this without going to thievery and stealing all of the tokens. And so we're going to send this over to our tool, and I'm not going to do this one in person. We've got a video for it, but it takes a little bit longer, and I just don't have time. And so this is how you would run the tool. And again, there's a demo of this online. But basically, you invoke Eros, you give it the name of the file that you want to attack, and then you also give it that query that we were looking at earlier. And then Eros is going to output something like this. So you can see that it's going to be another smart contract. And the important part is that attack function right there. And so what you can see is this attack function is going to do a couple of things. So first it's going to approve that this Uniswap pool has access to a large number of tokens, and then it swaps tokens for Ether. And so that means that it is inflating that denominator while simultaneously decreasing the numerator. And then because it does that to a point where the amount of collateral becomes 0, it's then able to invoke borrow without providing any collateral and asks it for all of the tokens in the lending pool. It gets those and then it transfers it to the message sender. And so this is just an example of the type of smart contract that we synthesize in order to show users what an attack can look like. And so that's all we're going to look at today. If you want any more information, you can look at our website. We also have a Twitter, apparently. And there's also GitHub repositories for the 2 tools that I showed you today.
Could you say something about what's the difference between your tool and Echidna, the way they do the randomization of the fuzzing kind of thing?
So we aren't doing fuzzing. So basically the way that, are you talking about specifically the first tool that I showed you or the second tool that I showed you? Or both?
The Eros was the second tool.
So the way Eros works is because we're not using fuzzing. When you use a fuzzing tool, you have to worry about is my fuzzer actually generating inputs that could end up showcasing an attack? So instead, what we're using is symbolic execution, and so we have a symbolic virtual machine that basically emulates the execution of the Ethereum, in this case, Ethereum virtual machine, and that's how it's generating the attacks rather than using fuzzing technology.
Okay, if I can ask a follow-up question. So for the symbolic engine, do you have any estimation of what's the size of a contract and start to hit the limit of the branching, number of branches?
Right, so you're talking about how large does the contract have to be in order to hit a path explosion, right? So currently this is a prototype, right? And so right now, we're primarily looking at toy examples. However, we're currently working on basically, improving the scalability of the tool. So, right now it's primarily toy examples, but we're quickly improving the path explosion problem. And if you're interested, I can tell you about some of the ways that we're looking into dealing with those issues.
Okay, thank you. I'll ask more later. Yeah.
Okay, any more questions?
Yep. So you mentioned that you are the founder and CTO of Veradice.
I'm one of the co-founders.
Oh, sure. Okay.
Yeah.
What's the business model of Veradice?
So the business model. So the business model of Veradice is we are a smart contract auditing company, and so writing specifications is difficult, which is why we feel comfortable providing tools, which is, I'm assuming, why you are asking, because we have these tools publicly available. And so essentially, we want people to use our tools, but also because we want to increase the assurances in this domain, but also we are aware that not everyone is capable of writing these specifications and also working with the underlying tools in order to ensure the verification procedures go through and stuff like that. And so that is, I guess, does that answer your question?
Yeah. Well, thank you for releasing the tools. That's awesome.
Yeah. So the question is, do you have a pricing structure for our services? And yes, we do. Basically, people can contact us, and it basically has to do with the amount of time that we think it would require in order to formalize a particular piece of or a particular project and then run them through our tools.
Okay. Then thank you so much, John. Big round of applause.